Thank you so much for the kind introduction. So, without further ado, I'll just get right to the point. So, at any point, if you feel, you can interrupt me in between and you can ask me questions pertaining to the slides that I'm showing. So, my slideshow is just for the sake of reference, but I will mainly be talking to you about the project and why we are doing the project. So, today, my topic is citizen science with 1 million galaxies. So the project, like it says, it aims to build a catalog of 1 million galaxies, which is 10 lakh galaxies. And these galaxies can be of any type. It can be a spiral, it can be a ring galaxy, it can be a bar galaxy. So we will show you the interface later on. But let me first give you a brief introduction about what I do and where I come from. So, like suggested, the Pune Knowledge Cluster is basically a project and now a Section 8 company which was established by the Office of Principal Scientific Advisor to the Government of India. So we advise the Prime Minister's office in the matters related to the science and technology. And we are one such science and technology cluster amongst 7 science and technology clusters in India. So now we are also hosted by IUCA. IUCA is the Inter-University Center for Astronomy and Astrophysics. So where I also work as an astronomer. And PKC, as we know it, has been set up in 2021. And since then, I have been working as a software engineer and a data manager in the big data and AI vertical of the PKC. So, when we talk about big data and AI, we truly deal with the astronomical data sets because the word astronomical can be taken literally as well as figuratively, meaning it really contains a huge amount of data. And with the modern telescopes that we are keeping on building and upgrading, we are generating more and more data than we can deal with. And there is a lot of data waiting to be looked at millions and millions of galaxies that people have never seen before. And the job of the astronomers is to look at them, find something completely new or find something quite peculiar, which may help us better understand or change our understanding of the morphology or the evolution of galaxies in general. So this is all very abstract. But what we really need to do is we need to be on our toes for near real-time discoveries because although astronomy is a field where you look at galaxies and stars and the light coming from them from billions of years ago, you need to be ready to look in the right place at the right time, and you should never miss a crucial discovery. So right now we have all this data, but we have a very limited computational and human resources that actually look at the data. Now, one way to speed up this process is make use of machines, but the machines cannot just understand how to understand or look at and decipher information from a given data on their own. So they need to be trained, and this training needs to be done in a systematic way. So the machine learning algorithms or machine learning techniques that are used nowadays make this process more or less automated. But this process also needs to be done right. It should not be hurried, and the scientific outcome should not be compromised. So the analysis should be rapid, but it should not be too ambitious to finish soon. So the goal is not to classify most number of galaxies. The goal is to classify most number of galaxies with the most possible accuracy. So that is the whole purpose of the 1 million galaxies project. Before we talk about the project, it's important to understand what we are looking at. So you all know the galaxies are a collection of stars, but that's not all. The galaxy contains stars, a lot of gases, a lot of interstellar dust. It contains a lot of unaccounted mass that you don't see, but you see the effect of that mass. So there are all these structures. There are gaseous halos, which are like bubbles of gas around the bulge of the galaxy. So what you see in front of you right now is a typical spiral galaxy. So actually, it is a barred spiral galaxy. This is pretty much how our Milky Way would have looked like if we had a very large selfie stick and we were able to take a selfie of our Milky Way galaxy. Now, notice that the sun is represented as a very small point, which is obvious because the solar system or the sun is infinitesimally small as compared to the size of this galaxy. Our galaxy is almost 100,000 or 1 lakh light years wide. So, although I say light years, it is actually a unit of distance. So, 1 light year is the distance traveled by a photon or a light in 1 year. So we all have studied in our schools that light travels at a fastest speed, which is about 3 lakh kilometers per second. Now, if you do the math and if you keep multiplying 3 lakh by 60 for a minute and then another 60 for an hour and so on and so forth, in 1 year, light will travel about 9.6 trillion kilometers. That is trillion with a 13 zeros. Now, this is the distance that light covers in 1 year. Now, if you take this distance and multiply it by 1 lakh, that is how big our Milky Way galaxy is in just kilometers, right? And our solar system is a very small part of that, lying on one of the spiral arms of our galaxy. And our Milky Way or Akash Ganga, in which we live, is one of many hundred billions of such galaxies that we see in our observable universe. So there may be galaxies or there may be objects that we have never seen before, but there is only one way to find out is to actually find them out. So we are developing a lot of modern instruments. So please tell me if I'm going fast, and please interrupt me if you have any questions at any point. So this is an actual photo. The earlier one was an artistic impression, but it was accurate. So it is how we have see, we have observed our Milky Way galaxy in all different regions, right? We observe our stars in our vicinity, and we have observed their motions, and we have modeled their orbits, and from that we have put together a picture with our understanding by looking at other galaxies, and then we have formulated the picture of the Milky Way galaxy. Because logically and obviously, we cannot take the picture of our own galaxy, but we can put together different parts of our galaxy like a name all those galaxies. So one such named is this whirlpool, which is obvious why it must have been named, because it really looks like a whirlpool or a a cyclone or a whirlwind. This is the galaxy I accidentally confused with this one. This is actually the Andromeda Galaxy, our neighbor. This is also captured by the Hubble Space Telescope. This is a barred spiral galaxy, just like our Milky Way galaxy, and it is only 2.5 million light years away from us. Now, this is about to collide with our Milky Way galaxy in another 2.5 billion years. So, and that is much before our sun will die, because our sun is scheduled to live for another 5 billion years. So how do we know all these things? So how do we know how long the sun is going to live, or how long the galaxies are going to take to collide? It is by observing something called as redshifts or blue shifts in their spectra. So we look at the light coming from the galaxies. We split the light that comes from these galaxies using something called as gratings or prisms, and then we look at the absorption lines and emission lines of different elements, and we compare them with the absorption lines and emission lines of those elements with the laboratory readings. And then we observe that, okay, the absorption lines or emission lines are either shifted towards the red part of the spectra or towards the blue part of the spectra. So if it is approaching us, then the spectral lines shift towards the blue part, which tells us that, okay, an object is approaching us, so it is receding. If a spectra shifts towards the red part of the spectrum, that is towards the larger wavelengths, then we deduce that the object is receding. I mean, it is going far away from us. So this is one technique. And then there are many more techniques by which astronomers study many galaxies and many stars at the same time, and we can tell with confidence about the life cycle and evolution of the stars as well as galaxies. So these are some more photographs of barred galaxies. So there are different kinds of barred galaxies. Some are lenticular, some are pure bar galaxies, some are barred spiral galaxies. So there are many variations and many different shapes, or what we like to call is the morphologies of the galaxies. So some spiral arms can be such scattered spiral arms, and this is a beautiful image captured by James Webb Space Telescope. It is NGC 1433, and it is about 46 million light years away. So it is almost 20 times farther than the Andromeda Galaxy. So we have indeed seen such beautiful galaxies and such beautiful images, and we have now recently sent the James Webb Space Telescope, which is the successor of the Hubble Space Telescope. And this telescope is actually performing pretty well. Hi, am I still there?
Yeah,
Can
yeah,
you
you're
guys
audible. Yes,
hear me?
yes.
Yes.
Okay,
Go
okay.
ahead.
Sorry, there was a power failure at Ayuka, and I was not sure if I would be disconnected, so I just
No issues.
switched
Go,
to.
go,
Okay, okay.
go ahead. Go ahead.
Sorry about the glitch. So this is a different kind of a galaxy. This is an elliptical galaxy. This is one of the largest galaxies that we have seen. It is very famous for another reason. So many of you might have seen a black hole image of the black hole right at the center of this galaxy. So the very popular and the only black hole image that we have captured has been captured by the Event Horizon Telescope, and it is this black hole that we have observed. So this is the M87, the largest and the brightest galaxy in the Virgo cluster. Now, while we were talking about morphology, so the whole purpose of running the 1 million galaxy project is because we want to catalog or classify the galaxies based on how they look. So, exactly what I said is called as the morphological classification of galaxies. So Edwin Hubble did this a long time ago. So he created this tuning fork diagram where he classified the galaxies based on their appearance and structure. So on the left arm of the tuning fork, you can see that there are elliptical galaxies. And as you head towards the right, they become more and more elliptical and less spherical. Right. As you go to the top arm, the galaxies start becoming pure spirals, and as you go towards the bottom arm, they start becoming barred spirals. Okay, and at the very end of the other end of the tuning fork, you will see that there are irregular galaxies. Now, is this the only are these the only types of galaxies that we see? So the answer is no. So we see all sorts of galaxies because we see them in their different phases. So some galaxies have just formed, some galaxies have just merged, some galaxies are merging, like the M51 galaxy, and some galaxies are sitting in silos and they are just growing old. So we have different kinds of galaxies. So these are some examples of lenticular galaxies or barred galaxies. This was cataloged by Sudhanshu Barve from Indian Institute of Astrophysics. So who is one of our collaborators in developing this project, along with Professor Ajit Kembhavi in Ayuka. These are some really cool galaxies. Now look at the features. So you can see very clear rings, right? So it is possible that these galaxies may have been spiral galaxies in the past, and they eventually have evolved in becoming ring galaxies. And we do observe galaxies transforming from one form to another based on the dynamics and all the gas activity that is happening around it, right? And another very important factor that is responsible for galaxies to become galaxies is what we believe to be dark matter. But we will not talk about that today. Today's talk is mainly about the classification of galaxies and how to do it with the help of citizen scientists, right? So today, you sit back, relax, and have fun in watching the different types of galaxies first. So it is crucial that you understand what are the different types and what are the different structures of galaxies that are out there. So if we show you some galaxy, it is crucial for you to know what are you really looking at, whether it is a spiral, whether it is a bar, whether it is a ring, or whether it is an irregular galaxy, or whether it is an elliptical galaxy, and so on. So these are some of the interacting galaxies. So these interacting galaxies are close enough to actually interact with each other by exchanging mass or by influencing their motion, right? So clearly, the M51 type is basically a spiral merging galaxies. Then there are shell ripple galaxies, which have a shell around a gas shell around the galaxy, central galaxy. Then there are dust lane ellipticals. Basically, there is a elliptical galaxy, and you can see a clear dust lane. So there is a very famous galaxy called Sombrero. So the galaxies pretty much look like that. So it is basically like this. So there is a dust lane. Can you see my pointer? Wait, let me switch it on. Yeah. So this is a dust lane, and you can see this hat-like feature, right? So this is a sombrero type galaxy. So it basically looks like a Mexican hat. Uh, this is another interesting image. So this image is a collection of a very small region of the sky, and Hubble had looked at a very small region in the sky for about a month. And then we have put together all the images that were captured by Hubble and have analyzed them. And there are only about, I think, 12 or 13 stars in this galaxy, in this image. Everything else is basically a galaxy. So this image is called as the Hubble Deep Field, and then there are about 3,000 galaxies which are present in this image, and some of them are exceptionally far away from us. we have seen a very interesting galaxy. I don't know if you are able to see, but there is a small red dot here. This galaxy is about 12 billion light years away from us, and this is one of the farthest galaxies that we have seen, and it is incredible. I mean, think about it, that just after about a billion years after the universe was formed, the dynamics were such that it was indeed able to form a galaxy. Now, this is something that we are still studying and trying to understand how it may have happened. So, there are about 2 trillion galaxies in the observable universe. And right now, post Vera Rubin, so we are building this telescope, which is already ready, by the way. So, everything is ready. Now, it is still in the calibration phase and instrumentation phase. But we have now designed a telescope which is 8.4 meters in diameter, and it has one of the world's largest cameras ever. And the job of that telescope will be to do a large scale synoptic survey. So it basically will look at the entire sky continuously, and it will keep doing sky survey again and again and again and again. And it will produce billions of high resolution images. And it will basically take 1500 HD screens to view one galaxy image, because that is the kind of the resolution that the camera will produce. And think about processing this data, looking at the individual galaxies. Just imagine the kind of images that this telescope will produce. Some of you might have tried clicking Andromeda or clicking Milky Way with your mobile phones or DSLR cameras. Just imagine the kind of the data that these observatories are going to generate in the next 20 years. Some of you are students, some of you might end up continuing research in astrophysics, and some of you might even study galaxies. So you are sitting on a gold mine. Today, you are waiting to see the release of many such mega science projects, and you will be dealing with data that nobody has ever dealt before. So we need to be ready. We need to keep up with all the incoming data, and we need to be ready with our tools to analyze it most effectively. Okay. So these are some of the multi-wavelength data sets, that big data sets that exist out there. And we are just looking at some of the data sets which are in the optical wavelength. So we have compiled the data sets from the SDSS catalog, and we are showing you small galaxy cutouts. And what you as citizens do is look at the galaxy and help us classify them. We of course are building state of the art instruments, and we are putting them out in the space, but we are also evolving the ground based capabilities. So these are just some of the existing, and some of them are also going to be upcoming missions. So there are hundreds of missions that have already flown or already set up on the ground so far, and then there are even tens and hundreds of more that we have planned based on our capabilities. So there is LSST, Large Scale Synoptic Telescope. It is also called as Vera Rubin Observatory now, named after the great astronomer Vera Rubin. Then there is 30-meter telescope, which will be set up on the mountaintop of Mauna Kea in Hawaii. Then there is extremely large telescope, which will be set up in Chile. And then there is Giant Magellan telescope. So these are some of the leading mega science astronomy projects that will generate a tremendous amount of data. So right now, the next generation data is going to create an immense amount of flood. And we currently, with if we keep processing the data that we do today, it is just not going to be processed ever. So right now, only few hundreds of terabytes of data is available. But very soon, petabytes and petabytes of data is going to be generated every month, which is just equivalent to the entire data that the internet generates, or the World Wide Web generates in a year. So just imagine the kind of the data that we will have to deal with. And this is not just a job of astronomers and students and colleges. It is also job of the industry to keep up with our requirements to handle this kind of data. Now, the first step is to be very logical and systematic about it, because You can't just jump on and build a huge infrastructure and expect that infrastructure to automatically process your data. The data processing needs a huge amount of intelligence. It needs a huge amount of understanding and intuition, and that intuition needs to be transferred to a machine, just like how the humans can have an intuition and they can look at a galaxy and tell that, okay, this could be a spiral, this looks like a bar, or this looks like a ring galaxy. So we definitely need a hand from the citizens as scientists, and we would, and that will only speed up the automation and the machine learning process, and it will help us build more effective and more sophisticated models to extract the appropriate scientific data from huge data sets. So citizens are supposed to very vigilantly and with the help of their curiosity keep up with the upcoming data releases. And once more and more galaxies are shown, they are supposed to classify them with as much accuracy as possible, because the goal is not to see, as a citizen, your goal should not be to classify all galaxies that we upload. The goal should be to classify the galaxies as accurately as possible. So we currently are showing you the data which has been captured from the 8.2-meter optical infrared telescope in Hawaii. It is called the Subaru telescope. It is a Japanese telescope, and there is a incredible instrument called Hyper Supreme Cam, and we are using the instrument. We are using the images captured by this particular payload on the Subaru telescope. So this is the structure of the projects that the project that we are running. So we have various partners and beneficiaries. So after this talk, you will be a part of this. So there are project students and interns. Then there are science enthusiasts like you all, and then there are citizens from all walks of life. They need not be students, or they need not even be related to science. So even a person who is a beautiful artist can join the citizen science project and look at galaxies and help us classify them. So you need not have any science background, you did not have any astronomy background, but it would be nice to have an interest in astronomy, because then you won't be bored to keep looking at galaxies and classifying them. So this is the timeline that we have had so far. So we have initially we handpicked some 50 astronomers that we knew personally. We asked them to test the platform, and we asked them to look at a certain number of galaxies and classify them. So based on their input, we then enhance the website, and we have kept the platform absolutely simple. So it is not at all very sophisticated. It is not even very attractive, to be frank, but it is very simple. Anybody can use it. And then the idea is to keep evolving this platform as per requirements, but it does the job. I mean, citizens can look at the galaxy very clearly, and then they can indeed classify the galaxy based on how it looks, and then that information is used by us at our end to train the machine learning model using what is known as a supervised data set. Okay, so going further, so we have been conducting a lot of online sessions. We also travel to different parts of the country to
Excuse me,
uh,
Atharva. Yeah.
yes.
Yeah. So actually, I will have to leave today for some other
Okay, okay,
meetings. Yeah.
no problem, no
Please
problem.
carry on. It's a wonderful
Yes,
thing.
yes,
And I will request all the students to interact with Atharva after the talk is over. Yeah.
definitely,
So we
definitely,
will be
no
in
problem.
touch, and I will talk to you later.
Sure, sure, no
Partha
problem
sir,
at all.
good
Yeah.
night for today. I will talk to you later, Partha sir. Yeah.
Okay.
Okay.
All
Bye.
right,
Bye.
see you, Gaurav. Bye.
Sure. Sure. Bye.
So we have been conducting such sessions all across India as well as online. So we have had road shows in Mumbai, Pune, Kerala, also in Delhi, and all the astronomy major astronomy meetings that we go to, like the ASI meetings, and ASI is basically the Astronomical Society of India, and other conferences. So this is how the interface looks like. So you can go to the website called CSA, Citizen Science and Astronomy .pkc.org.in. This is the website. So when you go to this website, you will see a homepage, and on the homepage you will be able to sign up and everything. You will find a detailed information on how to actually classify galaxies, and how we have also given certain videos on that website to understand the different types of galaxies, what is the importance of doing this project in the first place, what scientific value is there. So what happens to the data after you have classified the galaxies, and how do we use it. So and then there are other incentives also. So I will show you some examples in just a few minutes. So this is basically how the interface looks like. You basically see a galaxy image. You are supposed to identify only the features from the galaxy in the central part of the image. Okay, and then you should select all the features that you see, and it would be nice if you select all the features that you don't see as well, because this is an equally important data set for us. Okay, now in addition to that, you can add your additional comments, which are also very, very important for us. So let's say if you see this image, one could write a small remark that there is a blue dot that appears at the bottom right of the galaxy image. So that could be a useful remark probably. We will see what happens when you write such remarks, and we will talk about it a little bit later on. So this is also the profile page. So you can upload your picture, you can upload your details, and based on how many galaxies you classify, you will keep getting different medals. And at any point of time, you can download your participation certificate. So it can be automatically downloaded, and you can share it with the people that you have participated in the Citizen Science 1 million galaxies program. And the more number of galaxies you classify, the more will the number appear on your participation certificate. So it's really straightforward. It's not at all difficult. So for those who are interested in learning about the backend, so this website is a pure Python based website designed using Django backend. It uses MySQL database to maintain the galaxy images as well as the responses that citizens give. We currently are handling about 6 to 7 gigabytes of data of galaxies, and there are about 3 to 4 thousand users that are regular visitors to our galaxy classification project. And so far we have received about 350,000, which is about 3.5 lakh responses, or 3.5 lakh classifications. So we have been getting good response, but we really would hope that after this talk, some of you might be interested and you would sign up for this project. So we update the data sets not very frequently, but regularly. And then we collect the answers, and validated answers are then used by scientists to build the training sets for the machine learning model. So these are some old numbers. Now the number from 1700 has changed to about 3500 who have registered. And this ratio is more or less the same. So we have nearly 50-50 men-women ratio. So these are people from all parts of the country. Then there are, of course, international members also. So there are many active citizen science groups in our country. Many of them run online in the form of WhatsApp groups, and the people give us incredible response. So we are very lucky to have such an enthusiastic group of citizen scientists all across the country, and it is really fun and really amazing to interact with all of them. So these are some of the features that you can classify. So if you look at the platform, or if you look at the website, you will be able to classify the galaxies in all these different kinds. So there could be a spiral galaxy, there could be interacting galaxies which could be merging, or there could be a group of galaxies. Then there could be a dust lane, there could be a shell, there could be a tidal tail, there could be a bar. So all these are the different types of galaxies that you will see in the catalog. So based on the current responses, we have generated the following insights. So we have identified that to get so how many responses are required to confidently say that a given galaxy is a spiral galaxy. So how many people need to agree that a given galaxy is a spiral galaxy to confidently say that it really is a spiral. So we have determined based on the statistical analysis, initial statistical analysis, that between 30 to 50 responses, positive responses for a spiral galaxy are adequate to categorize the galaxy with 95% accuracy that it really is a spiral. So these insights have been useful. Then there are many more, much more sophisticated statistical insights, which we keep on generating based on the responses that we get with respect to time. So these are some of the feedbacks that the citizens have given. So the reason for using these two citizen science feedbacks are they are from the two far apart points of the country. So we have an international student from Bangladesh, and then we have a student from Kerala, and it was indeed interesting to see people from almost all the ends of the country to participate and actively complete the uploaded classification with good accuracy. So the reason for using their photos is because not only they completed the observations and classifications, but they did it with the fairly good enough accuracy. So which was very helpful for us. Then now it's time for a small break, and slowly we can conclude. So remember, I had shown you a photo of galaxy, and I had said that you can give your own remarks when you are classifying the galaxy. So this is one such example of that scenario. So this is a Dutch teacher. Her name was Hanny van Arkel. So she is an English teacher, and the image that she has seen has been an image of a galaxy. But in addition to that, she saw something pretty weird at the bottom of her image. So according to her, it for her it looked like a dancing frog. Okay. She felt that whatever object is there at the bottom of the galaxy looks like a furep. Furep is a Dutch word. So furep just means some blob or object, and she said that it looked like a dancing frog, and she just wrote a remark that there is a furep at the bottom of the image, so which is Dutch for object. So for many days, the image was not looked at, and the image sat in the responses database for a while. But then periodically, the astronomers do look at the responses that come from the various citizens. And after looking at this response, the astronomers asked the following questions. Well, is it real? Is there really a furep in the image? Is there some object in the image? Is there any other object like it? Then, whether or not is the object local, or what could be the origin of this object? Did this object get formed from a supernova explosion? Is it an unusual nebula? So we had all sorts of questions. Of course, I'm going to answer in a question what this object is. But then the astronomers were curious and they started asking all these questions because in the image the galaxy is very clear, but in addition to that galaxy there is a peculiar greenish looking object which really looks pretty much like a frog. So then they looked at other images of the same galaxy, and then they went back as long as 1953, and then they took a photographic plate and they developed the image from that photographic plate, and they observed that this object is there in 1953 as well. So it is definitely real. So this object was missed from the initial sky surveys and sites of astronomers because this object was also there in the 1953 image captured by the Palomar Observatory, which means that this object is really there in the sky. We don't know what it is, but it is definitely there. So then after many follow-up observations and many discussions and a lot of effort, scientists were finally able to figure out what exactly it is. So there is this spiral galaxy, this one. So the name of this galaxy is IC2497, and it was gravitationally interacting with a passing galaxy. So what happened is that when the galaxy was passing by, a large chunk of gas was pulled from the spiral galaxy by this IC2497 galaxy inside it. And while doing that, the black hole which was sitting in the center of the IC2497 got activated. So initially, the black hole was not doing too much activity. There were not too many polar jets, powerful polar jets coming out of its poles, magnetic dipoles. But then, when it pulled off a lot of gas, the gas started accreting around the black hole, and the black hole got activated again. And the light cone or the radiation that was thrown from the polar jets of the black hole or the quasar is basically a high energy object at the center of a galaxy. It is a quasi stellar object, just like pulsar is a pulsating star. Quasar is a quasi stellar object. It could be a black hole, it could be a neutron star, and it produces quasi stellar radiation. So what it did was it basically created this beam or a cone of light, and it ionized the portion of the gas surrounding the galaxy. And because of the ionization, the gas started emitting light. So you all know that when the gas ionizes, it jumps, the electrons in the outer shells of the gas jump to a higher orbit, and when they jump back, they emit some kind of radiation. In this case, the radiation was illuminating the gas surrounding the galaxy. Now, this galaxy, this gas surrounding the galaxy was then identified in many more such instances. We found many more such objects surrounding the galaxy regions, and this was a completely new class of objects. So we had captured these objects before, but we had never classified them. We had never studied them in detail. But just because a Dutch English teacher looked at a galaxy and she found some furep in the bottom of the image, and she wrote a remark, we were able to discover this completely new object. Now, this object is officially called as Hanny's furep. So Hanny was that lady's name, her teacher's name, and now we officially call that object as the Hanny's furep or Hanny's object. So, which is something incredible. I mean, all she did was she very sincerely and carefully looked at the galaxy images, and she looked for all these different kinds of artifacts or different kinds of features that she found interesting, and she reported them. And she discovered a completely new class of objects, and that is something incredible. I mean, this is the power that citizens have. You are looking at the galaxies that nobody has seen before, and you will be looking at some features that maybe everybody has missed before. So this is truly incredible. This is truly amazing to capture such kinds of information from citizens, because many a times there are a lot of galaxies which go overlooked, and if there are careful citizens who are looking at these galaxy images, then it creates a huge impact. So this was the small story. These are also the different kinds of outcomes, in addition to the obvious outcomes, which are training the machine learning models and helping us understand the morphological distribution of the galaxies in the sky surveys, which is a very important scientific use case for us. You can truly discover something completely new that nobody has seen before, just like Hanny did. So we would like to acknowledge all the contributors. So citizens have been performing very well. So these data sets are being curated personally by very big scientists, and we look at all the responses that you give. We carefully analyze the responses statistically, and we try to catalog the galaxies as accurately as possible. So I would like to invite you all to participate in this program, and not just participate in the galaxy classification, but if you are also interested in the science, please write to us. We would be very happy to get you involved and on board. So if some of you are interested in developing a website or a mobile application or such things, you are also welcome. You are also welcome on board. We can do, we can reach out this platform to a much more wider audience. And if you feel that you have better design capabilities, better programming capabilities to design or redesign this website or create a better looking application which is friendly for students or senior citizens, I would love to invite you all to work on that. So this is the current vision. So we want to make the very accurate and highly reliable data set for galaxies based on their morphology. We also want to make this data open source. So this data can then be used as a training data set for the upcoming Vera Rubin telescope as well as the other large telescope observations. So we really look forward to collaborating with a lot of students, scientists, and citizen scientists. And in the process, we also would like to learn a lot of new things from you. In addition to that, these citizen science projects are a great platform to talk about science and build scientific temper within the society, because it is not just enough to tell people what we do. It is also important to understand people and their thought process. And it is a job of the scientists as well as the researchers to communicate what work they do in the most effective way possible, so that the people also understand the intention and people also understand the actual science that goes on behind running these projects. So that's all from my side today. So I have nothing more to say. I would, however, like you to visit these websites. So this is our official website of Pune Knowledge Cluster. Then this is the website of the 1 million Galaxies project, which is also there in the QR code above. After my talk, I can share this presentation to you, or maybe Partha sir, and he will relate to you guys. I have already shared this link to Gaurav. So Gaurav will be able to share the presentation to you all. In addition to that, there are other citizen science platforms like Zooniverse, which you already might have heard about. So please feel free to participate in any citizen science program that you like. It is definitely going to help science group, and it will probably lead you to discover something completely new. So thank you everyone for patiently listening. I will be happy to take any questions that you have. So please feel free to unmute yourselves and ask questions.
Uh, are there any questions from the students? যদি কারুর বাংলায় কোশ্চেন করতে সুবিধা হয় বল, আমি তারপর অথর্বকে ইংলিশে ট্রান্সলেট করে দেবো। কিছু
Yeah,
প্রশ্ন
sure.
থাকলে বলতে পারিস।
So I have shared the link of the presentation in the chat. So feel free to share it with whoever you like. If you feel that you have any other questions later on, you can send them to me at this email ID, which is also given in the chat. But please mention the talk in the subject, so I will understand that it is a talk related question.
Sir, please
So
understand irregular galaxy.
So irregular galaxies are galaxies with no specific or a particular shape. So these irregular galaxies can be formed while mergers. So many a times the galaxies are formed because of a movement of a lot of gas inside the galaxies. So irregular galaxies are basically a collection of stars, dust, and gas. So, by definition, just like they sound, irregular galaxies are really irregular in shape. They have no specific shape, they can be in any random shape and size. So, eventually, as the systems become stable, the galaxies can form into a spiral or an elliptical or a ring or a bar galaxy. That is exactly what we are trying to understand with the help of such projects. So what happens with the irregular galaxies, and how are irregular galaxies formed? That is one of the science objectives for studying such large catalogs.
Atharva, I have a question, very nice question.
Yes, please tell me.
Is there any study about how do
Yes.
dark matter and dark energy influence the size shape of galaxies? Is there any study regarding
So
that?
yes, there is. So right now, what is happening is, so if you look at the structures of galaxies, they are spread across very large areas. And you know that gravity is a very weak force. So you all know that the gravitational force is directly proportional to the masses,
Okay.
but it is also inversely proportional to the square of distances, right?
Yeah.
So the stars which are so sparsely spread across, still influence the gravity, are still influenced by the gravity. And over a large time scale, the stars and the gases and the dust do manage to come together to form this huge area and region of a galaxy. Now, forming one galaxy is still enough or still possible. But now in the universe, you see huge clusters and super clusters of galaxies.
Yes.
So one of the explanations and one of the models
Hmm.
uh, best describes or best help understands this concept that in order to speed up the process of the galaxy formation, there needs to be some driving force or some driving gravity
Hmm.
which will bring together the galaxies together. So now you
To
all know
form a
that
cluster
the
or
universe,
supercluster. Yeah.
yes, to form a cluster or a supercluster.
Yeah.
So currently, that is what we believe is driving the galaxies to form such large clusters or such large clumps.
I understand.
Because we all know and we all have seen that the universe is expanding. But in spite of that, there are large superclusters forming. So, what is bringing the galaxies together? So, that is something that we call as a dark matter. So, we see the effect of the dark matter, although we do not see the matter directly, but we can indirectly detect some of the effects that the dark matter causes.
Okay. Thank you very much for the answer. Any more questions
No
from the
problem.
students? Any more questions from the students?
Sir,
So, do
Ha.
not feel shy.
sir,
Please feel free to ask any
Ha,
questions.
there is a question from Spandan. Yes, Spandan.
there are a lot of neutrino observatories in Ice Cube and in Japan.
Yes,
I know,
yes,
right?
yes. There
Uh,
is one in India
how
too,
do
in Kolar.
okay, okay. How those neutrino observatories help us to detect those
Okay,
galaxies?
so see, the neutrino events are caused by high energy processes. So, right now, as you and I are speaking, there are millions and millions of neutrinos passing through us. So, these neutrinos can come from our sun, they can come from other stars, they can come from other supernovae. So these neutrinos are very uh, low mass particles with a very high velocity, right? And they are also chargeless particles. So what we do is we build different types of materials which help us count the number of neutrinos that pass through a unit area. And depending upon the neutrino activity, you can tell what kind of particle physics and what kind of physical processes are undergoing inside the sun. And based on some correlations, you can tell what are the different activities also happening in our upper atmosphere. So whenever there are high energy events happening in the surrounding area, there are many high energy particles that are emitted. There are X rays, gamma rays, there are neutrinos, and then there are many more subatomic particles. So these particles are actually, you see, the indicators of different kinds of events or different kinds of physical processes that are undergoing. So that is why we build neutrino observatories and other atomic detectors and particle detectors. We also are interested in learning more about what we are made up of, and the more we keep studying the subatomic particles, the more number of subatomic subparticles are discovered day by day. So we are building more sophisticated and more energetic experiments to understand how and why are these particles formed. And we are indeed trying to find out answers to many unanswered questions. So neutrino observatories exist all over the world. The intention of building these observatories is to do scientific observations of high energy processes and understand why do these neutrinos originate in the first place, and why are there so many neutrinos being generated in all these different processes. So there is no one sentence answer, unfortunately, but I hope it answers your question to some extent.
Yes.
Okay, then the